Welcome to this tutorial on designing distributed software in mCRL2. The tutorial was recorded for the Discotech conference to be held on the 14th of June of 2021. In this tutorial we will introduce mCRL2, its process algebra, which is used to describe the behavior of systems, the modal mu calculus, which can be used to describe properties of systems. And we will do so using a series of mutual exclusion algorithms that was used for a similar purpose by Edgar Dijkstra in 1962 or 1963. The tutorial is presented by Jan Frieser Grote and me, Jeroen Keren. So let's first remember what mutual exclusion is. So in mutual exclusion, a number of processes are using a shared resource in such a way that only one process can use the shared resource at the same time. So for this purpose, we say that a process only uses the shared resource when it is in its critical section. And the aim of a mutual exclusion algorithm is now to guarantee that only one of the processes is in its critical section at the same time. The examples that we will use in this tutorial are all such that only two processes compete for access to the critical section. Now, the first algorithm that we introduce is a rather naive attempt at mutual exclusion, where each process has a shared variable flag that it uses to indicate that it is currently in its critical section. And then before accessing its critical section, it will wait until the flag of the other process becomes false using a busy waiting loop. So when the flag of the other process becomes false, it sets its own flag to true, executes the critical section, and when it's done, it sets its flag to false. Initially, of course, both processes are not in its critical section, so the flags are false. We'll see later on that this does not satisfy the mutual exclusion requirement, and you may already give a think as to why this is the case. Now, the first question is, how do we model a process like this in mCRL2? So for that, we first introduce the process algebra. Now, the basic building block in process algebra is an action. For instance, if we want to control a simple light, then we could have actions switch on and switch off. And generally, the actions are whatever happens on some sort of interface. Sometimes they are used to describe internal behavior as well. Now, actions are atomic, so they do not take time. And that means that if we want to model something which takes longer, then we need to split this action up into two parts, indicating the beginning and end of that action. For instance, if we want to model the execution of a critical section, we probably want to split it up into entering and leaving the critical section. Now, the behavior is described by combining actions. So the action A ultimately describes a label transition system where from the initial state, we can execute the action A and then successfully terminate. The sequential composition of two processes means that we first execute the first process, and then upon successful termination, we continue with the behavior of the second process. For instance, if we have the process A followed by B, we first execute A, and then we execute B. Then we can have a choice between two processes, which we encode using the alternative composition. And the alternative composition between two processes says we have the choice between executing the first process and executing the second process. So for instance, if we write A plus B with A and B actions, then we either execute action A and then terminate, or we execute action B and then terminate. And of course, we can combine this to obtain more complex behavior. Now, this only allows us to model very simple finite processes. So to model more complicated behavior, we can use recursion, where we introduce a name for a particular process expression, and that process expression itself can refer to such process variables. So for instance, if we want to model a machine that can do A infinitely often, we could say, specify this as the process P equals A followed by P, which is then a label transition system where in the initial state we can do an A action infinitely often by simply looping around. We need to be careful though, if we specify these recursive processes, we need to make sure that every process variable in the right-hand side is ultimately preceded by a action, which basically says the recursive processes need to be guarded. Now, to model more interesting behavior, we can parameterize processes and actions with data. So for instance, we can say that process 0 or process 1 enters its critical section, or that the answer is 42. And this allows us to model processes such as a counter, where we keep track of the number of times an up action happened, and we can actually report that number. So we model this as a process counter with parameter n, which is a natural number. And we then have a choice. Either we do an up action and we recursively behave as the counter process with n incremented, or we report the current value of n using a counted action, and then we behave as the counter process, leaving the value of the parameter unchanged. Now that we have data, we also want to be able to affect the control flow using that data. So suppose we want to extend the counter with a down action that can only be executed if up has been pushed at least once. Then we can do so by introducing a conditional. So we say that if n is greater than 0, then we can push the down button and we recursively behave as the counter with n decremented. Else we behave as the delta process, where delta represents the deadlock process, which cannot do anything. Now in this context, because we have other processes, other actions as well here in the alternative choice, this delta will cancel out, as choosing between doing some process X and deadlock is equivalent to choosing process X. The last ingredient that we have in the language is the sum. The sum generalizes the alternative choice over a variable over some arbitrary data domain here. So for instance, to extend the counter with a set action that can set the value of the counter to an arbitrary natural number, we can write the sum over all natural numbers set m. Now, I should point out at this point that the natural numbers in mCRL2 really are natural numbers. So if you would write down this process and try to generate a state space, then this would not terminate, as it simply tries to enumerate all natural numbers and it will keep going for a while. So in general, if you have some sort of infinite data domain here, you would like to restrict the actual values that you use using an if-then construct. So this gives us all we need to model sequential processes. So let's have a look how we use this to model the shared variables and the mutual exclusion algorithm from our example. Let's first focus on how we can model the shared variable. For that, we need to decide what type of shared variable we have here. And we are going to assume that the shared variables are atomic. So in that case, we can model the flag as a process where I simply keeps track of the identity of the variable and B keeps track of the current value of the variable. And we can now set the flag to an arbitrary Boolean value, or we can get the current value of the flag. You'll see that the set flag and the get flag actions here have suffixes R and S. These will be used later on in the communication between the shared variables and the mutual exclusion algorithms. So this models the flag. Then let's have a look at the mutual exclusion algorithm. Essentially, the mutual exclusion algorithm is a sequential composition of the different steps in the algorithm. There's one interesting aspect here, and that's the busy waiting loop. So observe that the busy waiting loop ends when the flag becomes false. And while the flag is true, there's no interesting behavior that we need to execute. We can model this in mCRL2 by relying on the fact that whenever two processes communicate, this communication will only succeed if both the sending and receiving part of the communication can execute the corresponding action. So in this case, this get flag that the mutual exclusion algorithm executes needs to communicate with a get flag that the shared variable executes. And this communication will only succeed if they agree on the value of their parameters. So in this case, this get flag will only succeed if the value of the shared variable is false. If the value of the shared variable is still true, then the mutual exclusion process here will block until this action becomes enabled. So that gives us a very straightforward way to model this busy waiting loop. And then the rest is simply setting the flag to true, entering and leaving the critical section, and then setting the flag to false. And then we repeat. So this gives us the basic ingredients, the sequential processes that we need to model the shared variables and the mutual exclusion algorithm. Now, how do we make these communicate? For that, we use the parallel composition. Now, the parallel composition between two processes as actions, in essence, are atomic, results in the interleaving of actions from both processes. So basically, the parallel composition of two processes will generate all interleavings. So in this case, if we execute A followed by B in parallel with C followed by D, we get a label transition system which gives all different interleavings. Now that's not all, however. We can also have the simultaneous occurrence of two actions, one from each process. So for instance, if from this state one process can do an A, the other can do a C, then we also have the multi-action where A and C happen at the same time. Of course, we also have this in all the other places. Now this can then be used to describe communication between two processes. So for instance, if these two processes communicate on B and C, so basically if B and C happen at the same time, they exchange some information, and say we refer to this exchange as E, then we can make this explicit. So we say that in this parallel composition, when this multi-action BC happens, the two processes communicate and the result is E. The effect this has on the label transition system is that every occurrence of this multi-action BC will be replaced by E. There is no other change in the semantics here. Now, of course, if we do this, we are typically interested only in the actions that do not take part in any communication, so A and D here in this case. You could think of those as external actions or external observable behavior of the system. and the result of the communication, where basically we want to enforce synchronization between the two, and we're not interested in B and C anymore. Now, we can make this explicit using the allow operator, which now says that we are only interested in these actions. So the actions B and C will be removed from the label transition system, and all multi-actions that are not explicitly specified here will also be removed. Now, of course, this may render part of the label transition system unreachable, and all those unreachable states are not considered either. And the result of this process is the one where the first process does A, then the processes synchronize on E, and then the second process can do the D, and then we have successful termination. Now we can take this setup and apply it to our mutual exclusion algorithm. So basically what we get are two instances of the mutual exclusion algorithm for process 0 and process 1, and instances of each of the flags that are executed in parallel, and the flags initially are false. The flags and the mutex processes communicate on the get flag and the set flag, where we say one party of the communication is essentially the receiving end and the other one is the sending end, and then the result is get flag. And we allow only the results of communication and the actions enter and leave that do not take part in communication. The result then is the label transition system that we see here on the bottom right. So to wrap up this part of the tutorial, let's have a look how this mutual exclusion algorithm can be analyzed in mCRL2 IDE. So mCRL2 IDE is the integrated development environment provided by mCRL2. So what we see here are process definitions for the flags and the mutual exclusion variables, mutual exclusion processes, as we saw them on the slides, as well as their initialization. Now the only thing we add here is the declaration of the actions, which carries their name and their type. We can now check if the specification is syntactically correct and well typed by pressing this cogwheel here, and the result will be reported at the bottom. So this specification is indeed well formed. Now if everything is well formed, we can generate the state space using the button here. And what it will do is it generates the state space, and it will then show a 2D representation of the state space in a new tool, LTS graph. Initially, the layout is a bit random, but we can improve the layout by using the automatic layout here by pressing start. So it will then use a spring layout algorithm to come up with a nicer representation of the state space. The initial state here is indicated in green. So we see here that we can start by having one of the two processes read the flag of the other process in this busy waiting loop. And we can then check that the behavior is as we expect it to be. Now, using a right click, you can pin states to the canvas, and if you drag, then the layout algorithm will adapt to this new situation. Now, in this first part of the tutorial, we have introduced the basics of the process algebra used by mCRL2. In the next video, we will introduce the modal mu calculus and show some examples. In the last part of the tutorial, we will focus on the actual modeling and verification of two mutual exclusion algorithms, namely Degger's algorithm and Peterson's algorithm.